There are three basic steps involved in producing a steel casting. 1. Cores and molds are made to create the shape of the part. 2. Steel is melted and poured into the mold. 3. The steel casting is removed from the mold and is ready for finishing operations, cleaning, machining, non-destructive examination, or other value-added services. The design engineer and the foundry engineer should work together to produce an optimized design that will benefit the customer. The design is used to construct the tooling called the pattern. Patterns are the shape of the design part and are used to shape the mold cavity. The kind of pattern needed to make the design part depends on several key factors. Number of castings to be produced, mold processes, dimensional tolerances required, and casting design. Generally, patterns can be made of wood, aluminum, cast iron, or plastic. Like any product, a steel casting can be produced most economically when the design lends itself to the process. Thus, a close relationship between the product designer and the foundry engineer is essential. The intricate shapes of many steel castings require careful analysis to ensure they can be cast using standard molding techniques. This is where the foundry engineer can help the design. Good castings start with good design. Both the user and the supplier should be in agreement on how the part will be manufactured. The location of the casting placed in the mold and the placement of risers, chill, and gates is important. Vertical surfaces in the mold need draft. Fillets help to eliminate stress points and improve casting integrity by eliminating hot spots. These are typical of some of the numerous details to be worked out by the design team. The design engineer, along with foundries, use advanced technologies such as rapid prototyping and computer-aided design tools. Special molding processes like investment casting and centrifugal casting offer unique value to designers. In regular steel casting production, the pattern is used to make a mold. The mold holds the liquid steel in the correct shape while it solidifies. While the mold is used only once, the pattern is used again and again. Important considerations in mold making include economical production in its design, surface finish, and dimensional capability. The most common material used in mold making is silica sand. The sand must be mixed with a binder to hold the right shape. Sand may be recycled. The most popular sand mixture used to make molds is green sand. Green sand is sand bonded with clay and water. Other binders can be used to make molds. Chemicals that bond sand together are called no-bake binders. The properties of bonded sand make it possible to use all types of mold-making equipment, from hand molding to high-production molding machines. Generally, sand is placed around the pattern, and in the case of clay-bonded sand, rammed to the desired hardness. In the case of chemical binders, the mold is chemically hardened after light manual or machine compaction. Molds are usually reproduced into two halves so that the pattern can be removed. The bottom of the mold is called a drag, and the top of the mold is called a cope. Sometimes the part design requires features which cannot be made in the mold alone. A separate piece of sand must be manufactured to make the design, and that piece of sand is placed inside the mold. This separate piece of sand is called a core. Cores are normally made out of chemically bonded sand. Once the core has been made, it is placed in the mold. Typically, the core is placed in the bottom half of the mold, the drag. Then the mold is closed by putting on the top half, or cope. Steel scrap must be melted and heated to almost 3,000 degrees Fahrenheit to make steel castings. There are two types of electric furnaces that are used to melt steel scrap. One is an electric arc furnace, where the electricity is passed directly through the steel through large graphite electrodes. The graphite electrodes are lowered into the steel scrap in order to melt it. These furnaces take about an hour to melt the steel. The second type of electric furnace is called an induction furnace. This furnace melts the steel by using an electrical coil. Electrical induction fields heat the steel. The induction furnace melting technique is normally used for smaller heats or special alloys. Once either type of furnace has melted the steel, final adjustments are made to the composition. A spectrographic analysis at the foundry's lab is used to make sure the steel composition in the furnaces is the specified alloy for the application. Argon oxygen decarburization, AOD, is a precise secondary refining process that is primarily used for stainless steels. It may also be utilized for applications that require special attributes of toughness, ductility, precise chemistry, and microstructure. Once the alloy adjustment is completed, the liquid steel that is in the furnace is tapped into a ladle that is used to pour the actual castings. The steel is poured from the ladle into the mold. After the pouring of steel into the molds, the castings are allowed to solidify and cool. The shakedown operation separates the steel casting from the mold and core sand. Once the casting is removed from the mold, it is ready for finishing and heat treatment. This includes blast cleaning, removal of risers and gates, heat treatment, welding, and machining. Blast cleaning is used at various stages in the finishing to remove adhering sand, oxide scale, and produce a uniform matte finish. Risers and gates used to make the quality castings must be removed. Since most cast alloys are weldable, welding may be used if required. Casting may be joined to other steel products by welding. Steel castings receive heat treatment to attain the desired mechanical properties, stress relief of the finished casting, or to produce the optimum corrosion resistance. Molding, melting, and finishing must be carefully managed to achieve the quality requirements needed. Today, 250 plants produce 1.5 million tons of steel castings each year. Today's design engineers use steel castings because they can obtain near-net shapes with the properties of steel at relatively low costs. For many parts, the only economical way to make the shape is to make a casting. With a steel casting, you get the high strength, toughness, and impact resistance of steel, which is not available with other materials. Abrasion, impact, and wear-resistant steels are easy to cast. They are difficult to fabricate or machine from bar stock. Other unique properties obtainable with steel castings are corrosion resistance and the ability to handle high-temperature applications using an ever-growing list of stainless steel alloys. Cast designs can produce parts as small as a heart valve or as large and complex as a turbine casing. Massive components of over 100,000 pounds are used in applications such as the giant dragline. Steel castings offer versatility of design with the strength and service performance of steel. Modern foundries are capable of producing this wide array of steel alloys for the designer's needs because of precise control in melting and heat treating. Many people are familiar with structural steel shapes commonly used in buildings, such as I-beams that are formed through rolling mills. The same good engineering properties are obtainable in steel castings. And like wrought steel products, castings can be welded, heat treated, and machined. The quality of the steel is tested through chemical analysis and mechanical properties testings of each heat. Modern non-destructive testing methods include radiography, ultrasonic, dye penetrant, and magnetic particle inspection that enables steel castings to be applied in the most demanding applications, such as nuclear power plants. The integrity of steel castings has been improved in recent years through the use of computerized analysis. Here is a foundry engineer using a software program designed to help understand directional solidification from the casting to the riser. After casting design is completed and tooling provided, modern foundries have the capacity to make multiple runs in relatively short time frames. It is this repeatability that makes the casting process so attractive. Short runs can be completed in a few days, providing considerable economic benefit to the casting customer. Cast steel parts are also welded or bolted into assemblies. They are frequently used where a unique configuration demands a special cast shape. Through heat treating procedures, special properties can be developed which are important to a specific section of the component. It is this flexibility that makes steel castings so important to the designer. Steel castings have been used extensively for dynamic loads. Steels are resistant to sudden failure because of their toughness, and steels are resistant to unexpected short service life because of metal fatigue. By varying the alloy composition, steel can handle high temperature and corrosive environments. Only steel affords this wide range of properties. Manganese steels exhibit a unique resistance to impact-type wear. The defense industry also takes advantage of steel castings in applications as diverse as tanks, armor, to ship propellers. As we have seen, there are tremendous advantages to be gained by designing the rugged properties of steel castings into a wide variety of industrial products. The consumer's team efforts of the equipment manufacturer and the foundry placed in the hands of the designer. Near-net shape for complex parts. Strength, toughness, and impact resistance. Corrosion resistance, high temperature and wear handling properties. Economical production of repetitive parts from ounces to tons. Single-piece components that can be welded, heat-treated, machined, and assembled. Reduced order cycle time. And finally, computerized design to ensure integrity. The foundry and the design engineer should work together to design a casting that can be made and used reliably and cost-effectively. In addition to mold and core making, gate and risers must be considered in casting design. The foundry must add a gating system for filling the mold with liquid steel. The gating system must allow the liquid steel to fill the mold cavity without eroding sand or splashing around. In order to make sure that the casting is sound, risers are added. Risers are reservoirs of steel that are placed on the steel casting to the offset shrinkage of steel during solidification. To do this, the riser must have a longer time of solidification than any part of the casting. It has to remain liquid in order to provide liquid metal to feed the casting as it contracts. The second requirement of the riser is that it must contain enough liquid metal so that it doesn't run out before the casting is solid. The third requirement of the risers must have a liquid path to feed the whole casting. The design of a casting requires not only consideration of the part requirements, but also design of the pattern and core boxes must allow the foundry to make high-quality, cost-effective, reliable castings. Draft permits the withdrawal of the pattern from the mold without breaking the sand. Draft is the taper added to the vertical sides of the pattern. The amount of draft should be recommended by the foundry. It depends on the depth of the pattern in the mold and the casting process to be used. The parting line is the joint of the cope and drag. The parting line affects quality and cost. It is usually placed at the largest cross-section of the pattern and of the casting. Patterns with straight parting lines, that is, all in one plane, can be produced easier at lower cost than those with irregular parting lines. Cores are used to create features that cannot be made by the pattern alone. This allows the designer to make complex internal cavities for part-like pumps. These cavities could not be made any other way. Cores allow the designer to include any complex shape in the casting design. The manufacture of the core, its placement in the mold, and its removal from the casting adds costs. Therefore, it is desirable to use innovative designs to reduce the number of cores required in any design. Designers should use the fewest cores possible in order to reduce casting costs and improve quality. Core prints in the mold hold cores in place in the mold and give access to remove the sand after the casting is made. Removing cores from casting cavities may be difficult when the areas to be cleaned are inaccessible. Designs should always take advantage of the manufacturing process. The designer can improve performance, quality, and cost through clever use of the manufacturing process.